Welcome everyone to the Climate and Environment Lightning Talks. My name is Jessie Krupski, and I'm a software engineer on the Environmental Insights Explorer team. I am super excited for this session where we'll have 10 lightning talks featuring projects that are using mapping tools for positive social and environmental impact. All right, let me explain the rules. So each speaker will only have 3 minutes to deliver their talk. We'll have a sign up front that will hold up when there are 30 seconds left, so the speaker knows that it's time to wrap up. At 3 minutes, on the dot, we'll hold up an applause sign where I need the audience to help us give the speaker a round of applause and let them know it's time to get off the stage and give the next speaker. So to fit in 10 speakers, we won't have time for questions, but if you have any questions, we encourage you to find the speaker during the break right after the session to continue the conversation. And with that, let's kick things off. So our first speakers today are Becky, Segal, and Madeleine Miller. They join us today from the Arctic Eider Society. Becky has been involved in Arctic research for 10 years, working with imagery from both icescapes and landscapes. With the Arctic Eider Society, Becky is a remote sensing coordinator for their platform SIKU, the Indigenous Knowledge Social Network, focusing on customizing ice and weather data for Indigenous communities and working toward detecting dangerous ice hazards with machine learning. Now, Madeleine specializes in cyber cartography and web mapping for environmental and social justice issues. After obtaining a postgraduate degree in advanced geomatics, Madeleine began working with the Arctic imagery analysis for the Canadian government. A passion for Indigenous-led research drew her to SIKU in 2021, where she has been developing mapping products ever since. Together, they are presenting enhancing sea ice safety and climate monitoring by mobilizing Inuit expertise and Earth observation data.
I'm Madeleine, and this is Becky. We're very happy to be here in person again this year after so long. We are here presenting on behalf of the Arctic Eider Society. The Arctic Eider Society is an Inuit-driven charity based out of Sanikiluaq, Nunavut in Canada, working with Indigenous communities across the North to facilitate Indigenous-led solutions and focus on self-determination in research, education, and environmental stewardship. In addition to our on-the-ground programs, in 2019 we launched SIKU, the Indigenous Knowledge Social Network. SIKU is a tool for Indigenous communities to access services such as weather, ice, and environmental information, as well as tools to run their own programs for research and environmental monitoring. To date, SIKU has over 13,000 users at scale across the North.
Oh, sorry, back one slide. SIKU is being used to show that communities can play a really important part in documenting wildlife and climate data at scale for the whole North. Users are making observations and sharing their knowledge about harvesting, ice and snow, trips, and more. This ice post shows a dangerous crack observed by Jonasi Ipek.
The annual SIKU Ice Watch enables users to use their own knowledge, language, and an advanced ice classification system to share information with their communities as well as others in real time, and facilitates knowledge transfer, language preservation, and safety on the ice. SIKU offers a number of different imagery layers as well, including high-resolution mosaics, up-to-date radar and optical imagery that are all accessed and processed using Google Earth Engine, and provide critical information for users about travel conditions on the ice, including potentially dangerous conditions.
The map layers are also available on both iOS and Android and include our very own SIKU Ice Map, which combines remote sensing and Inuit Kauyamajutukangit Inuit knowledge and ice observations in a way that's never been done before. The SIKU Ice Map makes ice charts accessible and uses them to show the landfast ice platform and the location of the ice edge, which is really important for safety in the winter. Real-time processing of radar imagery, including Sentinel-1 from Earth Engine, shows the roughness of the ice and helps facilitate trip planning, along with the ice posts made by local hunters. We're working on a new initiative that will help advance the Siku ice map by adding RadarSat constellation mission data, which is very similar to Sentinel-1, and to bring in machine learning to help identify open water areas within the sea ice platforms such as Polinias or Ikirasak or Sarvek in Inuktitut, which are really important for safety. Inuit observations made with the Siku app are going to contribute to ground truthing and training machine learning algorithms.
These interactions between Inuit...
Thank you very much. We're all very excited.
Thank you, and Madeleine. All right, thank you. Now, our second speaker is Charlotte Gohr. Charlotte is a research fellow at the Biosphere Reserves Institute at the Eberswalde University and is pursuing her PhD at the Leuphana University in Germany. Charlotte and her team use Earth Engine to quantify the temperature mitigation ecosystems. Her work with the Center of Econics and Ecosystem Management led to many temperature maps used by foresters to assess strategies to combat the consequences of climate change. After the conference ends, she'll be off on a 6-month research stay at the Jet Propulsion Laboratory, focusing on the tropical forest carbon cycle under climate change. Her talk today is Tracking Human Impact on Land Surface Temperature.
Hi, everyone. Thank you. So today I talk about heat extremes in Germany and with a special focus on forests. This map I produced in Google Earth Engine using Landsat data and collecting the means of hot days in 2021. This is an example area of Western Germany where you can clearly see the human impact on land surface temperature with hot cities on the top left and then this hot coal mine on the top right and then the coal mine on the top left in comparison to this cool riverside and the cool forest areas. How severely temperature rise can have an impact on land cover, I experience on a personal level. Since 20 years ago, I went with my family to Harz Mountains for a family vacation, and the little one, that's me, surrounded by this beautiful forest. And now 20 years later, the forest is gone. We went on a field trip last year to have a look at the results caused by temperature. The temperature rise caused a bark beetle outbreak, and most of the trees in the areas were gone. And then humans decided, or people in the area decided to clear cut all of the dead trees. And this led to, we also looked at the maps from Earth Engine, again, of the mean of the hot days in this year, and saw that especially the clear-cut areas are extremely hot in comparison to the remaining forest areas. Highways are another example of how humans are having an influence on the temperature on the landscape level. And you see this example of a highway with adjacent forests and dead tree trunks and gaps between the trees. Also, the temperature map shows the clear difference between this hot highway and adjacent remaining forest areas. This study was also used for a Greenpeace report supporting a protest against the new construction of a highway that was planned that 300 years old forest had to be cut down for this highway. We extended our regional studies to a large-scale analysis for whole Germany, and the data was used to support the background information for the climate protection plan of the newly built government in Germany last year. We also take our Earth Engine produced data sets back to the forests, and we meet foresters to discuss how to prepare forests better for climate change. Thank you very much.
All right, our third speaker is Erik Lindquist, Forestry Officer at the Food and Agriculture Organization of the United Nations. Erik specializes in processing large geospatial data sets to assist with analyzing, halting, and mitigating the effects of climate change. He develops computing platforms for remotely sensed data for autonomous land surface monitoring, especially in developing countries. His work aims to reduce deforestation and forest degradation and make better land management decisions. Today, he will be telling us about monitoring sustainable development goals with Google.
All right, thank you. Good afternoon, everybody. Just before I start, I want to acknowledge how awesome this event is, how fortunate I feel to be here, and how even after just the last 2 presentations, I feel a little bit better about the world than I felt maybe 5 minutes ago. So thanks to those 2 presenters, really awesome. If I leave you with one message today, it's just that the FAO is, oh, you can go back 1 slide, sorry, is that the FAO is busy using a combination of Google Earth Engine, open source softwares, and custom-built user interfaces to even further democratize access to valuable data and algorithms to enable locally driven results, hopefully better decision-making for a variety of social and environmental problems around the world. Today I'm going to talk about the Sustainable Development Goals and how we monitor the Sustainable Development Goals using this method. The SDGs, of course, are 17 focal areas or foci for making the world a better place, for humans or otherwise. We will choose one of them, in this case, SDG 15, or Life on Land, to speak about very quickly. And even more specifically, we will talk about SDG 15.3.1 and 4.2, both key indicators for environmental quality and resilience. 15.3.1 is the proportion of degraded land over all lands, and 15.4.2 is the Mountain Green Cover Index. At FAO, we are building applications, as I mentioned before, using Google Earth Engine, Jupyter, the Python API, shout out to the Python API, and voila, among other softwares to facilitate the local monitoring of these SDGs. Oh, okay, right, no speaker notes for these. I was like, what's going on? So here we have an example of the 15.3.1, which is the Mountain Green Cover Index. Users can access this all inside the CEPOL platform, provide their own, use globally available variables, or provide their own customized variables as needed. So you can do anything from basically a textbook result for this, or you can actually highly customize it using your own locally relevant inputs. This is another example of SDG 15.4.2, or Land Degradation Index, where you can build, this is an example over Bangladesh, where the entire country of Bangladesh was mapped for this SDG indicator. Very cool land transitions between time periods that can be built, charts can be built. And in this case, actually, there is actual real impact on the ground where degraded land was identified and restored using this application, this methodology. Come see us tomorrow if you want to learn more about this. If you want to try these out for yourself, we have a demo booth or a demo cubby or whatever it's called, demo table. And please come see us and talk about CEPOL and SDGs. Thank you very much.
Thank you, Erik. Now, our next speaker is Aurora Barone, a senior economics and policy analyst at the Environmental Defense Fund. She provides critical research and analysis to advance policy solutions addressing climate change. She performs spatial analytics to solve a wide range of environmental problems for applied research and public-facing applications. Aurora has previously worked as a research assistant at Columbia University's Earth Institute and at the Lamont Doherty Earth Observatory. She holds a master's in environmental science and policy from Columbia University. Aurora will be discussing with us building a climate vulnerability index.
Thank you, Jessie. So today I'm going to be talking about the Climate Vulnerability Index and how this GIS-based mapping tool can help improve our understanding of the intersection between vulnerability and climate change risks. So as climate change unfolds, the US is projected to experience a wide range of impacts and risks, from more frequent extreme weather events to a rise in infectious and chronic disease. Some of us will be more affected by those climate risks due to both greater exposure and a lower ability to prepare for, adapt, and recover from their effects. Our goal with our partners at Texas A&M was to disentangle which factors contribute to inequity so that we could empower vulnerable communities and policymakers to develop effective action plans. Unlike other environmental justice screening tools, the CVI incorporates more than 180 indicators, which include existing public health, social, economic, environmental, and climate data at the US Census Tract level. With the help of Google Earth Engine and other platforms, we were able to analyze large quantities of vector and raster data to develop a unitless index score that could be used to rank all census tracts in the US. Developed with community stakeholder input, the index integrates baseline vulnerabilities which reduce resilience with climate change impacts. If you lack access to medical facilities, live near an abandoned waste site, call a red line district home, or are without internet, these are just some examples of vulnerabilities that can make you less resilient to climate change. So let's take a quick look at where we are today in Mountain View, California. Immediately, we can see a few areas light up. So when you click on a census tract like this one in East Palo Alto, you'll get a readout of the overall CVI score, as well as the scores for each baseline vulnerability and climate change impact. The higher the score, the greater the vulnerability or risk. We adapted the approach that EPA uses with their Toxicological Prioritization Index, which utilizes a weighted average to aggregate data to provide an overall relative ranking, which is what you see here. We also included a radial pie chart profile to illustrate specific drivers of increased vulnerability. So for example, we see East Palo Alto and Menlo Park here. They're likely going to face similar climate-induced social and economic impacts as shown in the olive portion of the pie chart. However, East Palo Alto's baseline social and economic vulnerability, shown in teal, is much larger, meaning that it's not going to be as resilient as its neighboring community, even though it's going to be facing the same similar climate change impacts. So with this tool, we hope to help individual communities prioritize what is most needed for them to be resilient in this climate crisis. I'll just add, community feedback was really vital during this process, and we do invite collaboration. Thank you.
All right, our next speaker is TC. TC is an earth scientist in the Atmospheric Sciences and Global Change Division of the Pacific Northwest National Laboratory. He is working to improve urban representation and land models using various observational products, such as satellite-derived estimates and examining extreme events over coastal cities. He completed his PhD from Yale, where he developed a surface energy balance perspective to aerosol-climate interactions by combining theory and climate modeling. TC worked extensively on the urban heat island effect by using satellite measurements, crowdsourced weather station data, and conceptual modeling frameworks. He thinks cities will be the nexus for climate change adaptation and is interested in optimal strategies for minimizing heat stress and its disparities within cities. TC will be presenting Examining Urban Heat Stress Disparities in the United States.
Thanks, Jesse. And hello, everyone. It's great to be here. Over the past few years, many studies have looked at urban heat exposure disparities in the US using satellite data. Some results are shown here. In most cities, you see higher surface urban heat island intensity in poorer neighborhoods. Similarly, in most of the larger cities, the land surface temperature is higher in neighborhoods where people of color primarily live. However, satellites do not measure what we feel when we are outdoors. Satellites give the radiative skin temperature of what the satellite sees on the ground. Recently, we have been using crowdsourced weather station data over Europe to try to understand how well land surface temperature is associated with air temperature as well as heat index. The heat index is a metric which combines the impact of air temperature and relative humidity on human thermal discomfort. And what we find is that it's not that well associated. Recently, we found that as the surface temperature increases within cities spatially, the heat index doesn't actually budge much. So the question is, how useful are disparity estimates of heat exposure based on land surface temperature? It is difficult to estimate air temperature and especially heat stress from satellites at these scales. So instead, we move to numerical modeling. In one of our projects, we ran a land model with a 1 kilometer forcing data constrained by observations. So this data set has an urban representation. In another project, we ran a fully coupled model with more complex urban representation over the Great Lakes region at 4 kilometer resolution. The model results were then ingested into Google Earth Engine for further analysis. The model simulations show that there is pervasive disparity in heat index within US cities, and you can see that with all the pink dots on the map. However, the magnitude of these disparities, and this is more easy to understand if you look at the plot on the right for Chicago, is higher for skin temperature than for air temperature or more physiologically relevant metrics of heat exposure or heat stress, such as heat index and wet bulb globe temperature. As you can see, the slopes are steeper for skin temperature. This means that we should be careful about using land surface temperature to get quantitative estimates of disparities. However, there are opportunities to combine these satellite measurements with ancillary data to provide more accurate estimates of heat exposure. Plus, land surface temperature is still useful to understand other aspects of local urban warming. Thank you for your time, and thanks to all of my collaborators. We can talk more later.
All right, our next speaker is Meenakshi Kushwaha. Meenakshi is an environmental health researcher, consultant, and educator. Her current research is on developing air quality models using stationary and mobile measurements in India. She co-founded ILK Labs, which has a growing list of collaborators, including Google, CSTEP, University of Washington at Seattle, and UC Berkeley. She has worked on several environmental health issues, including lead poisoning, air quality, and water quality. Her work on pollution inequities in India was recently featured in the New York Times. Meenakshi graduated with an MPH in Environmental and Occupational Health from the University of Washington, Seattle. She began her career in biomedical research, which continues to inform her current work. Meenakshi is passionate about open science and loves using open source environments for data analysis, visualization, and reporting. Meenakshi will be telling us about mapping air pollution over Bengaluru mobile monitoring data.
Thank you, Jesse. Hello, everyone. It's so wonderful to be here. Please help me and raise your hand if you've been to Bangalore. Great. So today I'm going to talk about air quality mapping in Bangalore using GEE. And if you've been to Bangalore, you know it's a mega city, more than 10 million people. With more than 10 million people, that's a lot of people. It's a dense city, and that means there's a lot of traffic. And with traffic, there's a lot of air pollution. But the scale of air pollution, or where the air pollution is, like where is it and how much, we don't know exactly. And we don't know that exactly because the instruments that measure air pollution, those monitors can be really expensive. So we have very few regulatory air quality monitors in the city. So to address this problem, what we did is we used lower cost sensors, put it on a car, and then measured pollutions on the road. And we used that data to build air quality models for the entire city. So that's what our setup looks like. We have a CNG car, which is a cleaner car, fitted with sensors for different pollutants, obviously GPS for location data, and a probe for weather data. And with that, we measured PM 2.5 that you may be familiar with, black carbon, which is a subset of PM 2.5. When we burn fossil fuels, we get black carbon, and ultrafine particles that are nanoscale particles that enter deep inside, that can enter deep inside our lung and into our bloodstream. So we measured all of these concentrations on the roads of Bangalore city. And when we do that, we get the on-road data that you can see on the left. That's a map of concentrations, on-road PM 2.5 concentrations for every 50-meter road driven. And that map is showing 1,000 kilometers of road, a portion of, that's just 10% of Bangalore. So we combine those observations with other factors that influence pollution, like population, point sources, vegetation, weather. And even though I've just shown you 4 categories here, I'm talking about hundreds of variables that we have to consider for several buffer lengths. And it's such an advantage to be able to extract this data on the cloud using Google Earth Engine instead of trying to do this on your computer. So if you could do it in weeks, we could do it in days. If you could do it in days, we can do it in hours using GE. Then to make a model that can help us estimate citywide pollution, giving us maps like this for PM 2.5, for black carbon, for ultrafine particles. And for the first time ever, we have a really high resolution on-road data, best estimates of on-road pollution, and a whole picture of that for a megacity like Bangalore. Thank you.
All right, our 7th speaker is Mothes, a research associate with the Geospatial Centroid at Colorado State University. Dr. Mothes works to further develop research, education, and outreach programs for the Geospatial Centroid, which is Colorado State University's Center for Geospatial Technologies. She is an avid programmer who conducts spatial analysis, creates spatial data visualizations, and builds interactive web mapping applications for both on- and off-campus clients. She also develops education materials to increase access to geospatial methods and technologies. Caitlin received her PhD from the University of Miami while developing and applying spatial tools for biodiversity conservation efforts and policies. Her work now ranges in topics such as environmental justice, wildfire impacts, and climate resiliency. Today, Caitlin will be presenting leveraging earth science data to heighten awareness of environmental injustices within the US prison system.
All right. Hi, everyone. I am with the Geospatial Centroid from Colorado State University, where we are essentially the center for all things geospatial at CSU, providing geospatial services for a wide range of on- and off-campus projects, and also more recently carrying out our own projects, one of which is the topic of today, which is a NASA-funded equity and environmental justice initiative we are doing in collaboration with the prison agriculture. Oh, can you go back? Slide. Thank you. Which is where we are utilizing the power of geospatial analysis and earth science data to heighten awareness of environmental injustices within the US prison system. And while often overlooked for various reasons, prison injustice is a big problem in this country. I wish I had an hour or more to talk about it, but I only have about 2 minutes left. But US prisons are, by definition, EJ communities, as they are highly overrepresented by people of color, indigenous persons, low-income individuals, and there's a growing body of work heightening awareness that prisons are often disproportionately subjected to adverse environmental threats, such as climate extremes, poor air quality, toxic exposure, of which prisoners have no choice but to endure. And so, however, prisons as sites of environmental justice is still highly understudied, and there's a real need for more empirical evidence to support positive change regarding these EJ issues. So what we are doing is using satellite data and their ancillary products to characterize the environmental harms faced by prisoners, prison staff, and the surrounding communities, using geospatial analysis to quantify the conditions at the prisons and their surrounding landscapes. And we are examining all state and federally run US prisons, and we'll be quantifying or characterizing the environmental harms in a standardized way by producing a comparable environmental vulnerability index. And we're calculating this index by measuring a wide range of indicators of environmental burden, which are grouped into these 3 components shown here: environmental exposures, which includes things like distance to toxic facilities, environmental effects, which includes things like air quality metrics, and third, climate risk, which includes variables like heat index, or shown here, wildfire risk. These 3 components are averaged to produce a single environmental vulnerability index. And this methodology is based off of that of previous EJ platforms and initiatives. So what this project will produce is an open source geospatial data set that we hope will be incorporated into current EJ platforms, such as the EPA's EJ screen, or we could get more funding to produce our own platform specific to prison environmental injustice. So this work is still highly preliminary, so stay tuned. But if you want to get in touch, this is our contact info. This is the type of work we do, the Geospatial Centroid, or you can reach out to me throughout the rest of the conference. Thank you.
All right, our next speaker is Alexa Lopez. Alexa works as a remote sensing analyst, helping to create and visualize data produced at Cloud to Street. She graduated from Texas State University with an undergraduate degree in Geography, Resources, and Environmental Studies, and a master's degree in geography with a focus on remote sensing. Her background includes the mapping of aquatic vegetation with high-resolution imagery and work with NASA Develop that used Earth observation data for urban heat mapping. Alexa is interested in improving scientific communication via data visualization by eliminating barriers to understanding the data and making information relevant and usable across disciplines. Her talk is Dynamic Flood Mapping for Resiliency, using Google Earth Engine to create decision-ready tools with local and global stakeholders.
Thank you so much, Jesse. So my name is Alexa Lopez, and I work for Cloud to Street. A little bit about us: we're a flooding intelligence platform that utilizes private and public satellite data, machine learning, and local data to provide insights on impact, coverage, and the severity of flooding. So we've worked with small and large companies alike and have been data providers to government entities like NASA and the World Food Program. And in August of 2021, Cloud to Street data was used in a paper that identified a significant increase of the world's population exposure to flooding from 2000 to 2018, and this was featured in Nature. When our founders, Bessie Schwartz and Dr. Beth Tellman, were in grad school, they learned about Earth Engine and felt this could be an effective way to track flooding in near real time using satellite imagery. Across the country, Dr. Colin Doyle was doing similar work, and over time in these niche circles of science, the founders met Dr. Doyle, and our company's been built on fostering and promoting science communication ever since. Through all stages of our company's growth, we've used Google in some capacity as an early prototype for our dashboard analytics, as a way to validate data produced quickly during emergency response, and we used the Google Cloud Platform to help scale our AI, which was a significant improvement in our accuracy metrics. Most recently, we are thrilled to have Google host the Global Flood Database, which was created in partnership with the Dartmouth Observatory, and this shows major flooding around the world from 2000 to 2018 using Mothes and can be found in the Earth Engine catalog now. We now have a dashboard which provides historical data on flooding and maximum flood extents. It can be seen up there. And we can also we've evolved to a point where we're able to provide our users with weekly and bi-weekly reports on the impact flooding has in their regions of interest. In the pursuit of promoting equitable science communication, I'd like to think we'll work with anyone on anything. And with that, I mean we'll speak to users on their preferred platform, meet at their preferred frequency, and work with their budget by either securing additional funding from humanitarian aids or modifying the product to fit their needs. Because of this, we've worked with over 20 governments that use our data in times of disaster, and they've been able to secure over $13 million in disaster response funding. An example I have of this is at the beginning of the year, Tropical Cyclone Gombe heavily impacted the east coast of Africa and most notably Mozambique. Over a 7-day period, we identified over 15,000 people to be living in at-risk areas of flooding and identified over 200 square kilometers of inundated agriculture. During March the 15th through the 22nd, we were able to communicate with members of the World Food Program and serve as a source of validation at a time when the Mozambique government was receiving very different ranges of the reports of who was affected. So during our debrief with the World Food Program, they told us that we were able to provide them with critical insight on the mobilization of aid and relief in regions that were most affected by the flooding, according to science. Presently, we're continuing to work with governments and humanitarian partners, and we're closely monitoring the media coverage of flooding. Thank you.
Looks like we had a couple slides left. All right. Now, our ninth speaker is Arjiro Kavada, a NASA program manager for Sustainable Development Goals. Arji is an atmospheric and oceanic scientist leading NASA's effort to extend uses of Earth science research and applications to promote sustainable development in alignment with the UN SDGs. She is the founding executive director for the International Earth Observations for Sustainable Development Goals initiative. RG also leads NASA's expanded partnership with Google on air quality research and applications. She holds a doctorate and master's degrees in atmospheric and oceanic science from the University of Maryland, a master's degree in applied mathematics and statistics from Georgetown, and a physics bachelor degree from Johns Hopkins. She's also a certified change management advanced practitioner. Dr. Kavada will be sharing with us improving societal benefits through enhanced air quality monitoring.
Hello, everyone. So hopefully people are still awake and engaged. Really excited to be here with you today. I know Rebecca in her morning welcoming talk highlighted a lot of the collaborations between NASA and Google and other partners. She mentioned OpenET, the collaboration with NASA's Revere and FAO on the deforestation work, and we'll be hearing later about the work with the Navajo Nation. And so today I'm really excited to talk to you about some existing work that we've been doing for the last year or so to help improve air quality forecasts and estimates, leveraging both NASA's and Google's capabilities and also different data streams. And so to do that, as a first step, we've started by, Google has helped integrate some new NASA data sets like the GEOS composition forecast model into the Earth Engine catalog. And so this is a system that produces global three-dimensional distributions of atmospheric composition at the 25 square kilometer resolution. And so one of the things that is available through this ingestion of the GeoCF dataset is a replay, a meteorological replay of time averaged 1 hour data. And so the teams are now working to help downscale some of these, these data sets by leveraging both satellite observations, for example, from Tropomi or MAYAC, in addition to Google's Air View project data sets and other resources to help really improve the spatial resolution and make these forecasts more relevant and available to local communities and decision makers. And there is also a process for validating this work by leveraging independent ground observations. In addition, another part of the team is also working is looking at another data set, the MERA-2 data set, which is a global atmospheric reanalysis data set. And so they are looking at PM2.5 data. And so they've been working and combining this with ground data from EPA's air quality sensor system to help both bias correct and also help downscale the MERA-2 PM2.5 data sets from a coarser grid of 0.5 degree to a finer resolution of about 1 kilometer. And so this is a very exciting partnership. And so as next steps, we're hoping that we can then collaborate with the NASA USAID's Revere program to help bring some of these capabilities and data sets to other regions around the world, like the Mekong region in Southeast Asia. So tomorrow, my colleague Callum Wayman will be giving a demo on the GeoCF dataset and how it is available on the Earth Engine catalog. So I invite you to join that. And with that, I'm going to close. And thank you very much, everyone.
All right, last but not least, our 10th and final speaker is Ifosa Aragbasa, joining us today from the University of the Free State in South Africa. Dr. Aragbasa is an accomplished scholar with a deep interest in physical geography and geospatial science, with a particular focus on biogeography, ecological modeling, climate change, advanced remote sensing, and geographic information systems. He uses computer programming, big data analysis, and cloud computing applications in the mountainous regions. He'll be talking about the Mountain to Mountain Research Project with the University of the Free State and the Appalachian State University. Today, Dr. Aragbasa will be sharing monitoring the effects of climate change on grassland succession in a mountainous and protected area.
Thank you very much. I'm going to be making a presentation on the monitoring the effects of climate change on grass land succession in mountainous region. The first part of this research has already been published in the PLOS ONE journal at the beginning of this year by myself and my host at the University of the Free State, Professor Geoffrey Mukwege. The second part of the research is trying to see the effect of climate change on the changes in the species within the park. That's the study area over there. It's called the Golden Gate National Highland Parks, located in South Africa near the Lesotho border. Now, the study made use of random forest machine learning Earth engine to classify these grasslands. Using several data sets, you find more information about it on the paper we already published. Now, looking at the effects of climate change, we use two variables, precipitation and land surface temperature, which we derived from Mothes images and Landsat data. And the climate data was derived from the CHIPS data, which is all available on the Earth engine profile. Now, these are some of the results showing the changes in temperature over time using the time series analysis on Earth engine. As you can see on the graph there, we try to look at it, showing the changes over time in years and then within the months to see how the temperature shifted from one point to the other. Now, looking at the precipitation data, we find the same thing occurring in that particular area, saying that the rainfall also is shifting within the park. There is a small reduction, which we also try to calculate the SPI to see how dry the area is. You can see the dip in 2015 where we had a drought in South Africa at that time. Now we try to measure all these data sets to the changes in NDVI within the area, where we try to look at the magnitude of the shift using the sand slope to see how much greening and browning is going on within that particular area. Now we use these climate data to try to understand how it's affecting the succession within the park. Now we found that there are 12, when we mapped the park, there were 12 dominant species, but 4 of the species, which cover about 15% of the park, were seriously affected and replaced by other species. And when we looked at it, we found out that mostly precipitation and land surface temperature had the most effect on predicting the changes. So I would like to just appreciate my collaborators and my host, Professor Geoffrey Mukwege at the University of the Free State. Thank you.
All right, so looks like we're actually a little bit early today, but we are heading into a break now. So if you have questions for any of the speakers, for our in-person attendees, I encourage you to find them and ask them during this break. And so with that, let's give one last round of applause to all of our speakers.